Hello everyone and welcome to our 18th class. Today I'm gonna go over the materials that are gonna be covered on your second exam. We are gonna have an exam review and I will have a few slides to talk about the materials that are gonna be covered, and then I have a compilation of the previous examples that we have gone through in the past few classes. The second exam will cover chapters 5 and 6 of your textbook. Nothing that was covered on exam 1 will be covered with a direct question in this exam. The exam is on this Thursday, March 24th at 4:30 p.m. in Moodle. We have 90 minutes. The exam will become available to you exactly at 4:30, and you will have up to 6 p.m. to do the exam. Please make sure to upload your work showing how you find the final answer to each question, and also you need to upload your cheat sheet. All rules are identical to the previous exam, so let's take a look at some of those in the next slide. You can use any calculator in this exam. Similar to the previous exam, this one is closed book and closed notes, but you can have a letter-sized cheat sheet. You can write, type, or pretty much however you want. You can populate or fill out this cheat sheet. You can write whatever you want except for solution to a specific problem. And I want to be clear here that you can have steps, solution steps, but I don't want to see numbers and like exactly the solution to one question. If you need to use any table, those tables will be given to you, so you don't need to worry about putting tables on your cheat sheet. Equations are not going to be given to you, so all the equations that you need are supposed to be on your cheat sheet so that you don't have to memorize them. Of course, we are not allowed to use cell phones on this exam, and again, keep in mind that the exam will be available exactly at 4:30 on Moodle, and it's gonna be available up to 6 p.m. and then um, it's gonna be closed. So make sure that you plan well for the exam. Keep in mind that pretty much 10 minutes or so of the 90 minutes, I have allocated that additional time for you so that you can gather your solutions on your sheets and your cheat sheet and everything, and take photos of them and upload them on Moodle. So you really don't need 90 minutes to do the exam. 80 minutes is more than enough, and then 10 minutes is going to be there for you to pretty much gather everything and upload them on Moodle. So now let's go through the examples that we have. So I'm going to go through some examples. You have seen these before. These are important examples, and I expect you guys to be very good in those and know how to go through them. The first one, we have a traffic flow relationship where V is equal to 60 minus 0.2K. The question is asking about maximum capacity of traffic volume. So it wants you to find the maximum volume that you can see. So why don't you think for a couple of minutes about it and then continue with the video. So we know that V is equal to 60 minus 0.2K. We also know that Q is equal to K into V. Just to refresh our memories, V is the speed, K is density, and Q is flow rate. So what I will be doing is to derive an equation that gives me flow rate based on density. So if I want to do that, I just multiply both sides by K. So if I do that, I'm going to have KV on the left hand side, or Q, and on the right hand side I'm going to have K into 60 minus 0.2K, or 60K minus 0.2K squared. So what you need to do is to find the maximum q. If we take the first derivative of this equation and set it equal to 0, we are going to find the k at which the maximum or minimum q is going to be observed. So we do that, and if you solve that equation, k is going to be equal to 150 vehicles per mile. So this is the density at which this is the density at which we expect to see maximum flow. So if you want to find maximum flow, you need to plug this value of density back into this equation. So that means that you're going to have 60k minus 0.2k squared. You just put 150 for k's. Your maximum flow rate is going to be 4,500 vehicles per hour. Problem 2. Consider a 1-hour traffic flow of 120 vehicles. An analyst is interested in obtaining the distribution of 1-minute volume counts. What is the probability of having between 1 and 3 cars arriving, and what is the probability of having more than 6 cars arriving in each 1-minute interval? So pause for a couple of minutes, think about this problem, and then proceed with the video, please. So the arrival rate is given to us. It's 120 vehicles per hour. Here I'm converting it to vehicles per second. So you just need to divide it by 3600. That's going to give us 0.033 vehicles per second. Lambda t is equal to 0.033 vehicles per second into 60 seconds, or 2 vehicles per minute. Now you need to remember that this is a Poisson distribution for arrival of vehicles, and you pretty much need to find different parameters for Poisson distribution and plug it back into the equation. So lambda is either 2 vehicles if you go with the approach that I showed above that converts vehicle per hour to vehicle per second, or you can just divide 120 vehicles per hour by 60 and get 2 vehicles per minute, and then just multiply it by 1 minute and get 2 vehicles arriving in each minute. So the probability of having 1 vehicle is 2 to the power of 1 into e to the negative 2 over 1 factorial, so it's 0.2707. Probability of having 2 vehicles, you just multiply, or we just put the values into the equation. For n equal to 2, you find it. You do the same for 3, and then the summation of those 3 numbers would be the probability of having between 1 and 3 vehicles arriving there in 1-minute intervals. So the value would be 27.1 plus 27.1 plus 18, or 72.2%. This also can be expressed as 0.722 in terms of probability. So in the next part, we want to find the probability of having more than 6 cars arriving. So that would be 1 minus probability of having less than or equal to 6 cars arriving. So that's 1 minus probability of 0 plus probability of 1, 2, 3, up to 6 cars arriving. Just need to add those numbers, and 1 minus 0.995 is going to be 0.005, or 0.5%. Problem 3 is on deterministic queuing. After observing arrivals and departures at a highway toll booth over a 65-minute time period, the observer notes that the arrival and departure rates are deterministic, but instead of being uniform, they change over time according to known functions. The arrival rate is given by lambda t equal to 2.2 plus 0.17 t minus 0.0032 t squared, and departure rate is mu t equal to 1.2 plus 0.07 t, where t is in minutes after the beginning of the observation, and lambda t and mu t are in vehicles per minute. So keep in mind, these are not arrivals in units of vehicles. These are arrival rates in units of vehicle per minute. So determine the total vehicle delay at the toll booth and longest queue, assuming a DD1 queuing. So first thing that we need to do is to find cumulative arrival and departure based on arrival rate and departure rate that we have. So arrival, I'm going to call it A of t, is the integral of lambda t dt from 0 to t. It's 2.2 plus 0.17 t minus 0.0032 t squared dt. If you take the integral of that, you're going to get this term here. For the departure, we are going to do the same thing. So it's the integral of mu t dt from 0 to t. You take the integral and you get this term here. So if you want to find queue lengths, if you know the cumulative arrival, cumulative departure, you subtract departure from arrival, you get the queue length. So we will do that. The queue length is going to be given by this term here, negative 0.00107 t cube plus 0.05 t squared plus t. If you want to find maximum queue length, you need to take the first derivative and set it equal to 0. That is going to give you times at which the slope of q is 0. So that could be maximum or minimum queue length. So if you take the first derivative, you're going to get negative 0.00321 t squared plus 0.1 t plus 1. You say it equal to 0, you're going to get two numbers. One is going to be between 0 and 65. The other one is going to be outside. So the one that is between 0 and 65 is going to give you the time at which the queue length is going to be maximum. So you're not done there. You need to find the actual queue length. So you need to plug 39.12 into the equation for Q. When you do that, the maximum queue length is going to be 51.58 vehicles. If you want to find the time at which Q dissipates, you just need to set Qt equal to 0, or that means that AT minus DT is equal to 0, or they are equal to each other. So if you do that, you pretty much are setting this term equal to this term. You know, you don't need to take the integration again. So if you do that, you're going to have negative 0.00107 t cube plus 0.05 t squared plus t equal to 0. This is the figure as it looks. And that is going to give you a t of 61.8 minutes. So that's the time at which Q is going to dissipate. If you want to find delay, you just need to find the integral of AT dt from 0 to 61.8 and subtract the integral of dt from 0 to 61.8 from it, and that, if you do all the math, is going to give you 1925.8 vehicles minute. Problem 4, we have a 6-lane urban freeway on a 6% upgrade that is 1.5 mile long. Lane width is 11 feet. Obstruction 2 feet from the right edge of the travel pavement. You have 9 ramps within 3 miles upstream and 3 miles downstream of the midpoint of the analysis segment. So you have 9 ramps in a total of 6 miles. Traffic stream consists of primarily commuters, so your F sub P is 1. Directional weekday peak hour volume of 23 vehicles is observed, with 700 vehicles arriving in the most congested 15 minutes. You use this information to find peak hour factor. If traffic stream has 15% large trucks and buses and no RVs, what is the level of service? Let's start with the base conditions. The lane width is 11 feet. Minimum right shoulder lateral clearance is 2 feet. We have 15% heavy vehicles. We have 9 ramps within 6 miles. 6% upgrade, and the length is 1.5 miles. And driver population is dominated with familiar users. So F sub P is going to be 1. Let's estimate the free flow speed. We are going to use the equation that we have. So free flow speed is equal to 75.4 minus F sub LW minus F sub LC minus 3.22 into total ramp density to the power of 0.84. So we're going to use table 6.3 and 6.4 to find values for F sub LW and F sub LC respectively. So with table 6.3, lane width is 11 feet. You can see that based on the table, we are on row 2 because that row includes 11. So F sub LW is going to be 1.9. Using table 6.4, obstruction is 2 feet away. And number of lanes in each direction is 3 because this is a 6-lane freeway. So based on the table, F sub LC is 1.6. Now we estimate the free flow speed. To do that, we need to know what is the total ramp density. Is 9 ramps over 6 miles or 1.5. So we plug everything into the equation and our free flow speed is going to be 67.4 miles per hour. We round this value to the nearest 5 miles per hour, and that is going to give us a free flow speed of 65 miles per hour. Now we want to determine the flow rate, or V sub P. The equation is V over peak hour factor over number of lanes over heavy vehicle factor over driver population factor. So PHF, we know that it is equal to V divided by the maximum 15-minute volume into 4. Our hourly volume is 2300 vehicles per hour. 700 vehicles were seen during the 15-minute with the highest volume. So if you do the math, your peak hour factor is going to be 0.821. Number of lanes is 3. F sub P is 1. What we need to do is to find F sub HV. So because this is a specific upgrade, we need to use this table. And there were a few things that were given to us. One was the slope and the other one was the length. So the slope was 6% upgrade. So we are going to be on this part of the curve because this part includes 6. The length was 1.5 miles, so it's more than 1. That means that we are on the bottom row of this part of the table. And the percentage of trucks and buses was 15. So the intersection of this row and that column is going to give us a value of 3.5 for passenger car equivalency factor. So P sub T is 0.15, E sub T, we just found it from the table, is 3.5. We don't have any recreational vehicles or RVs, so P sub R is 0. So we just plug everything into this equation, f sub hv equal to 1 over 1 plus pt into et minus 1 plus pr into er minus 1. Pr is 0, so this part is going to be 0, and the rest, we have them. If you do the math, f sub hv is going to be 0.727. What f sub hv is going to do is that it will convert flow rate that is stated in vehicles per hour to flow rate that is stated in passenger cars per hour. So V sub P is equal to capital V over PHF over N over F sub HV over F sub P. That is 2300 divided by 0.821 divided by 3 divided by 0.727 divided by 1, which is our F sub P. That's going to give us 1284.5. We round it to 1285 passenger cars per hour per lane. So what we need to do is to put that volume, 1285 passenger car per hour per lane, on this figure. Go and use the curve that is corresponding to our free flow speed, which is 65 miles per hour, and based on the intersection of the curve and the volume, find the actual speed. So let's do that. So this is 1285. I'm gonna go up. You're gonna see that when I intersect the free flow, the speed flow curve, it has not bent yet. As a result, our speed is gonna be equal, or happens to be equal to the free flow speed, which is 65 miles per hour. So now we can find density. It is flow rate divided by speed. 1285 by 65, it is 19.8. So that's going to be our density. And as a result, when you go to the table, you would find out that our level of service is going to be C.